Hi there, in this video I'm going to go through the derivatives of inverse trigonometric functions. So let me title this Derivatives of Inverse Trigonometric Functions. So let me take a red pen and a ruler, underline this. First of all, let me give the first result. So the first result reads, if y equals the inverse sine of x, so if you have y equals sine inverse of x, or the inverse sine of x, okay, then dy over dx, its derivative, so dy over dx will be 1 over the root 1 minus x squared. Okay, so that is the result for the inverse sine of x, or sine inverse of x. Okay. Now, in addition, let me show you how that result is derived. So let me go through the proof. So proof. So I'm going to break the proof down into stages. So here's step number 1. So first of all, let me start off with y equals sine inverse x, and in step 1 we rewrite that, so we could rewrite that as sine y is equal to x. Okay, so that is step number 1, rewriting the equation that you have. Okay, now in step number 2, since we're proving a derivative result, we're going to differentiate both sides with respect to x. So in step number 2, by differentiating both sides with respect to x. Okay, so what do I mean by this? Well, we're going to work out d by dx, the derivative with respect to x of the left hand term, sine y. And we also need to differentiate, so d by dx of the right hand term, which is x. So that is what I mean by differentiating both sides with respect to x. So we need to differentiate both the left hand as well as the right hand term with respect to x. So that brings us to step 3. Now, in the last video, so I did two videos on implicit differentiation, and one of the notes that I've made on that video is that if you want to differentiate a y term only with respect to x, we need to use a chain rule. Okay, so on the left hand side, I'm differentiating a y term only, so I'm differentiating sine y with respect to x, so I've called that star. I'm going to calculate star as a side calculation. So let's calculate d by dx of sine y as a side calculation. So once again, I have a y term only, and to differentiate a y term only, we need to use a chain rule. Okay, so we need d by dy of the y term multiplied by dy over dx. Again, if you're not clear about this step, have a look at the video that I did on implicit differentiation. It should be the video before this one. Okay, so if I differentiate sine y with respect to y, differentiating sine is cos, so you're going to get cos y times dy over dx, or cos y dy over dx. Okay, so that is the solution to star. And if I replace the left hand term by our solution here, okay, so let me call that step 4, we're going to have cos y dy over dx appearing on the left hand side, and that is equal to, when I differentiate x, it's 1. Okay, so we're nearly there. So we need to prove the result for dy over dx. So if I rearrange, dy over dx will be 1 divided by cos y. Now, at this moment, we have dy over dx in terms of y. We need to rewrite this in terms of x, okay? So ideally, if we could write this cos y term in terms of sine y, we could go back to this stage, step number 1, and replace all of the sine y terms by x, okay? So we can do that by using a trigonometric identity. So I can take a trigonometric identity and write cos y in terms of sine y, and by doing so I can replace all of the sine y terms by x's, okay? So I'll call that step number 5. So the identity that we're going to be using is this one, cos squared y plus sine squared y, that is equal to 1. So we're going to use the fundamental Pythagorean identity. Okay, so let's rearrange the identity for cos y. So if I rearrange, cos y will be, okay, the square root of 1 minus sine squared y. So if I go back to step 4, so if I replace the cos y term by the root of 1 minus sine squared, let's see what we have. So in this case, dy by dx, that is equal to 1 over the square root of 1 minus sine squared y. Okay, so that takes us to the next step. So now from here on, we can replace all of the sine terms, or the sine y terms, by x's in order to conclude the proof. Okay, so in step 6, since sine y is x, so that means dy over dx is indeed 1 divided by the root of 1 minus, and sine y is x, so sine squared therefore is x squared. And that concludes the proof. Okay, so that is the derivation of the derivation for y. If y equals the inverse sine of x, the derivative of the inverse sine of x function. Okay, so that is the derivation for the derivative for the inverse sine function. The derivation for the remaining two functions, y equals inverse cos and y equals inverse tan, follows the same method. Okay, so let me take another sheet of paper. So I'll call this number 2. So if y equals cos inverse x, dy by dx should be minus 1 over the root of 1 minus x squared. So it's similar to the sine inverse result. Okay, so with the cos inverse result, the derivative has a minus in front. Okay, so let's prove this also. So proof. So in step number 1, start with y equals cos inverse x. So that is what I did earlier with the sine inverse proof. So in this case, y equals cos inverse x, and if I rewrite, cos y is equal to x. Okay, so that is step number 1. Let's remind ourselves of step 2. So earlier with step 2, differentiate both sides with respect to x. So let's repeat over here. So if I repeat that stage, d by dx of cos y on the left, that is equal to d by dx of x on the right. Okay, so once again I'm going to name this term star, and we're going to do that as a side calculation in step 3. Okay, so we need to differentiate the y term only, cos y, with respect to x. So we need to use this idea again. So we need to use the chain rule to differentiate that y term only. So we differentiate that y term with respect to y, and don't forget to multiply that by dy over dx. So let's do that as a side calculation. So here is star d by dx of cos y. So that is a d by dy of cos y times dy over dx. So if I differentiate cos, that is minus sine. So minus sine y dy over dx. So that's the outcome of star, the term on the left hand side. So let me use that result in step number 4. So in step number 4, so this is what I did earlier. I replaced the result from the side calculation in this step here to come up with this stage. So let me repeat the process here. So when I do the replacement, I'll have minus sine y dy over dx is equal to d by dx of x, which is 1. And if I rearrange for dy over dx, dy by dx will be 1 divided by, okay, minus sine y. Okay, so once again, once you reach this step, you need to use a trigonometric identity to write sine y in terms of cos y, so that you can replace all of your cos y terms by x's. Okay, so that takes us to the next step. So let me continue on the reverse. So step number 5. So the identity for us is the same one as before. So we're going to use the Pythagorean identity. Cos squared y plus sine squared y is equal to 1. Okay, but in this instance we need to rearrange for sine y. So if I rearrange for sine y will then be, okay, the root of 1 minus cos squared y. Okay, and if I replace that dy by dx, so if I replace sine y by the root of 1 minus cos squared y in the previous equation, we're going to have dy by dx, and that is minus 1 over the root of 1 minus cos squared y. So that takes us to the last step, step number 6. And now we can replace the cos y terms by x to conclude the proof. So since cos y is equal to x, that means that dy over dx is indeed minus 1 over the root of 1 minus, so since cos y is x, cos squared y therefore is x squared. So that completes the proof. Okay, so that is the proof for the derivative of cos inverse x. Let's do the same. So the proof of the derivative of tan inverse x follows the same method. So let me give you the result first of all. So result 3, if y is equal to tan inverse x, dy over dx should be 1 over 1 plus x squared. So let's prove this result also. So using the same steps, step number 1, start with this equation here. So y is equal to tan inverse x, and when I rewrite, tan y is equal to x on the right. Okay, so that is step number 1. Remember step number 2. So step number 2, so if you look at the previous derivation, we need to differentiate both sides with respect to x. So step number 2, we need d by dx of tan y, the left hand term. We also need to calculate d by dx of x, the right hand term. And let's calculate the left-hand term in step 3 as a side calculation. Okay, so let's work out d by dx of tan y. And once again, you have a y term only, so we need to use a chain rule. So we need d by dy of tan y, multiply that by dy by dx. Now if you remember, when you differentiate tan, you're going to get sec squared, so sec squared y, in this case, dy over dx. Okay? So in next step, so in step number 4, if I replace star by what we have here, we're going to end up with sec squared y dy by dx, and that is equal to, when I differentiate x on the right, it's 1. And if I therefore rearrange dy by dx will be 1 divided by sec squared y. Okay? So once again, we need to write our answer in terms of x. So if I can write this term here in terms of tan, I can replace all of the tan y terms by x's. So once again, we need to use a trigonometric identity to help us. So over to the reverse side, here is step number 5. So the identity for us is, we're going to be using 1 plus tan squared y is equal to sec squared y. So this is the identity for us. And if I do the replacement, dy by dx, so if I replace sec squared y by 1 plus tan squared y in the previous equation, we're going to end up with 1 divided by 1 plus tan squared y. So that takes us to the last step, step number 6. And now we're in the situation whereby we can replace all of the tan y terms by x's to complete the proof. So in step 6, since tan y is equal to x, so therefore dy by dx is indeed 1 divided by 1 plus x squared. So that completes the proof. Okay? So here are the steps, and here are the results for the derivatives for inverse functions, as well as the proofs of those results too. And that also completes this video. So I hope you found this video helpful. If you did, a like will be appreciated. It will be greatly appreciated. And just have a look at the steps, practice the derivations, and I'm pretty sure that you'll get there